Well, tonight's a monster night for multiple reasons, and the first monster reason is that tonight is a very special lesson. It is our first BC only topic of the year. We're not completely done with all of our AB topics, but we are. This one fits in here nicely tonight, and so the next couple of nights are going to be BC only topics, and what they do is they fall into a category called Advanced Integration Techniques, and tonight specifically is called a technique where we use integration by parts. So, and then we commonly just refer to it as parts. Will be the technique. Now, we do have our formula down here in the box. Why there's a cow in the box, I do not know. I can't explain that, but I did see that on Google, and I had to import it. And but this is our formula we're going to use tonight. It's the integral of u times dv is equal to uv minus the integral of v du. Now, if that sounds like it was in Chinese, great. That's awesome. I wouldn't expect anything less. But we're going to dive in, and I think we're going to be pretty darn good at this by the end of tonight. Alright, just to gain an appreciation for this crazy formula and this crazy rule comes from, we are going to invest some time into a proof. It's not something that we have to be an expert at, but I think anything that you can take away from this proof is gravy, and I think it's going to deepen your understanding down the road. So what if we had the product of two functions that were in terms of x, so both u and v are in terms of x. So really when I say u, I'm thinking of something like u of x, or v is really v of... Whoops, let me start over with that one. V is really v of x, they're functions of x. And let's say I wanted to take the derivative of those with respect to x. We would certainly grab our product rule and we'd say, well, it's u times the derivative of v with respect to x plus the v times the derivative of u with respect to x, right? Okay. Now what if we wanted to undo what we just did? In order to undo it, we would integrate both sides. So what if I just slapped an integral on both sides? Alright, nothing special here. One of the things you're going to notice is we are going to have some pretty exquisite handwriting, and I'm going to try to be ultra careful tonight with my stylus pen, just so my U's look like U's and my V's look like V's. I want to try to make the V's very crisp. Okay, now, if I integrate here, you'll notice that the integral and the derivative knock each other out, and we simply get the product of uv, which is what we were shooting for. We were trying to undo what we had just done. And then I'm just going to express this one on the right as the sum of two individual integrals. Alright, so the integral of v times du dx. Alright, now what I'm going to do is I'm just going to rearrange some of the terms, because my big idea tonight is I want to try to get this one by itself. So I'm going to rearrange some of the terms and so forth, and here's what it's going to look like. I'm going to say the integral of u times the derivative of v with respect to x is really uv minus the integral of v du dx. So you'll notice I kind of rearrange, move some terms from side to side and so forth. And this is ultimately our formula tonight. Now we're going to shorten it up a little bit. We generally disregard the dx's, so we would generally write the integral of u dv is equal to u times v minus the integral of v du. And ladies and gentlemen, this is our new big fancy formula for tonight. This is called integration by parts, and we are going to be good at it. Well, a great question to ask yourself right now is, how in the world do I know when to use integration by parts as opposed to just using a very simple u sub type of problem? And I want you to compare these two problems here. If I said x times e to the x squared, that would be an old school u sub problem, because if you let u equal the exponent, the derivative is 2x, and what you can anticipate now is that x is going to knock out that one, and we're just going to end up integrating e to the u. But in order for those u subs to work out, the term that I have right here had to be just right, you know, and if there wasn't an x there, we were up a creek without a paddle, so to speak. So the parts are going to make us more versatile. For instance, what if the exponent was just x? You know, would a u sub as we know it still work? And the answer is no. So basically, this is going to make us much more versatile when it comes to integrating. You know, our world with regards to integration is about to, expand tenfold just because of the new technique we have. Now, generally, to paraphrase here, if you're integrating the product of a polynomial times what we call a transcendental function, and I'll try to spell that out, transcendental. if you see the product of these two types of functions, then it's a good time to use integration by parts. Now you're wondering, what in the world is a transcendental function? I've never heard that phrase before. Well, it's basically anything that's not a polynomial. Think of transcendentals as non-polynomials. You know, something like an exponential function or a natural log function or some kind of trig function. You know, they all fall into this oddball category called transcendentals. So, you know, polynomial is, of course, you know, something like x squared or, you know, polynomial. So now we're going to get down to the nitty-gritty, and we're going to really formulate a game plan on how to attack these rascals. Now tonight, it's our job to not only pick a U, but you also have to pick a DV, alright? So we need to make 2 assignments tonight, not just a U, but a DV. And are we going to screw this up once in a while? Absolutely. Sometimes I still see ones where it's just, you got to just pick a U, go with it, and see if it takes you somewhere. And there's going to be multiple times where we hit a dead end and we go back and we switch them. Alright, now here's probably the most useful thing. We're going to start by picking a U. That's what we're going to start with, according to the phrase liate. Alright. So this little acronym or mnemonic, whatever you want to call it, is going to help us determine how to pick our U. And it goes in this order. Start by looking for an L, or a logarithmic function. If you have a logarithmic function, boom, that's your U, go with it. Now, if you don't have a logarithmic, look for an I, which stands for inverse trig. And there you go. So if you see like arcsine or arctangent, bang, that's your U. If you don't have one of those, look for A, and that's going to be an algebraic function, or I like to call them a polynomial function, but the A fit the mnemonic better. T would be just a generic trig function, something, you know, non-inverse, just like sine, cosine, or tangent. And then the E would be your exponential functions, okay? So that's the order we're going to go in as we try to choose our U. And then by default, the DV will be whatever expression is left over, okay? So DV is going to be whatever's left over. Then once we make those assignments, then we're going to calculate or compute our DU and our V by hand. Now, if I give you U, how are you going to find DU? Yeah, you're going to derivate. Okay? But if I started with DV and you needed to get V, then you're going to integrate. So we got a little bit of deriving and integrating going on at the same time, and we're going to really have to talk ourselves through these in order to nail these. Finally, are you ready to try one? I'm going to go back and I'm going to pull the integral that I introduced you to earlier. How do we integrate x times e to the x power with respect to x? Now, I'll be the first one to tell you, when I'm in the middle of a test, you know, I don't go into the problem hoping that it's integration by parts per se. It's usually not the first thing on my mind. You know, I might have tried some other thoughts first before I got to the point where I said, you know what, I think it's going to be integration by parts. One of the keys is, we said it is the product of a polynomial function times a transcendental. So that's another giveaway that might lead you in the right direction. Now I'm going to start with my U here, and I'm going to see, okay, liate, I don't have any logs, I don't have any. In fact, let me write this out here really quick for you. Let's go liate, and we'll cross them off in order. I don't have any logarithmic functions. I don't have any inverse trigs, but I do have an algebraic function, and that's my x. So I'm going to let u equal x, whose derivative is simply 1 times... Oh my goodness, did I write a u there? You can probably hear Bailey dropping his bone on the tile floor, so hopefully that don't bother you too much. Then whatever's left over, what did we not use in the expression? And that was the entire e to the x dx. So don't forget about the dx. Don't sleep on that dx. That's important. And then if I integrate both sides, I'll get v equals e to the x, which is quite convenient. Alright, now did you remember our formula from earlier? Let's go ahead and just rewrite our formula. We said that the integral of u times dv is equal to u times v minus the integral of v du. Alright, so let's just pick our u, which we said was x. Our v was e to the x. And then we need to integrate v times du, which in this case was dx. So now we still do have an integral to evaluate, but it's so much simpler and more manageable. So I'm going to say my final antiderivative is x times e to the x minus e to the x plus c. And that, ladies and gentlemen, is the antiderivative. How could we check our answer? Well, it's pretty easy. All we got to do is derive this rascal and see if it gives us the original function that we started with. And it wouldn't be a bad one to derive. It really wouldn't take me too long. I do a very simple product rule, derive this single term, combine like terms, and we're done. Alright, are you ready for round 2? Check out this nasty looking integral. Let's integrate x cubed times the natural log of x. Alright, and we're going to try to pick our u, and I'm going to just go through the phrase liate. And let's see, do we have a log function? Ding, 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 winner, winner, chicken dinner. That's my u right there. And his derivative is going to be 1 over x times dx. You know, really take pride in good notation. Make sure your dx is in there. So we've already used that up. So what's left over? dv by default has to be x cubed times dx. Who, if we integrate dv, just remind yourself you're integrating right there. V will then be 1/4 of x to the 4th. Alright, don't worry about the plus c, that'll come on the final answer at the end when we're all done. Now the formula says I need uv, which in this case is going to be the natural log of x times 1/4 x to the 4th minus the integral of v times du. So that's going to be 1 over x dx. And we just got a little bit of cleaning up to do. I'm in no big hurry here, so we're just going to say I'm going to put these in a more common order. We'll put the polynomial in front of the log minus the integral. Put the 1/4 out in front, and I'm going to cancel an x and get x cubed. Alright, we're now ready to integrate the much simpler integral. 1/4 x to the 4th natural log of x minus. Now this is just going back in time to our old-fashioned power rule. It's going to give me 1/16 for a coefficient, x to the 4th. Now we throw our plus c on there, and this is our final antiderivative. The next thing I want to introduce you to is a definite integral using integration by parts, and it gets a little messier just because there's so much going on. But here is the proper notation for a definite integral using integration by parts. Here's the proper notation for a definite integral using integration by parts. Okay? And notice what's going to happen here is, you start off with your bounds a to b. Now that first term you get doesn't involve an integral anymore, so you got to throw the bounds on in using this notation, and then minus, then you do have a simpler integral using the same bounds right there. So let's go try one just like it. Alright, the next problem I got up my sleeve for you is a heavy hitter. We're not going to hold any punches back here. Besides being a definite integral with bounds of 0 to 1, I want to integrate arctan of x with respect to x. So we're going to start off by trying to pick a u. And so we consider liate, and we don't have a log, but yes, we do have an inverse trig function, so u is going to be arctangent of x. So here's great review. Do you remember how to derive arctan? Great review right here. It's going to be the derivative on top, which of course derivative of x is just 1, divided by 1 plus your inner function squared. Okay? That's your derivative. And of course, almost forgot the dx at the end. Now your dv is going to be whatever's left over. What's left over? What didn't I use? Well, we didn't use the little dx yet. And if we integrate both sides, we're going to get v's equal to x. So that's very important. Alright, so now what's my integral say? It's going to be uv with bounds. So it's going to be x times arctangent of x with bounds of 0 to 1 minus the integral of v du. So it's going to be x all over 1 plus x squared dx, again, bounds of 0 to 1. Now, we certainly have our work cut out for you. I told you we weren't holding any punches here. What I'd like to do is kind of, not worry about that first term just yet. And what I want to do is just really work on integrating the second term. Now, in order to, if I just gave you this integral a month ago, we would have said, let's let u equal the denominator. Do you remember that? And then, our du would be 2x dx, and, by the time I solved for dx, you could start to visualize the x down here canceling with the x on top, and you'd end up integrating, du over u. Okay, so I'm kind of doing that all off to the side. In fact, we're at that stage of the game where if you can successfully do that entire u substitution in your head, more power to you. I'm going to encourage you to do it, believe it or not. So the antiderivative, because it's du over u, is going to be the natural log of u, but in this case, my u was 1 plus x squared. Now, what kind of coefficient do you think I'm going to have in front of that term? Don't forget about the 2. Don't sleep on that 2. So it's going to be a 1/2 as a coefficient, and my bounds on that term are going to also be 0 to 1. Now, because I've got both terms have the exact same bounds, which is pretty common, I'm going to just go ahead and I'm going to plug a 0 in, or I'm going to plug a 1 into everything. So I'll do that in blue. I'm going to plug a 1. I got 1 times the arctangent of 1 minus 1/2 the natural log of 1 plus 1, okay, minus, now I'm going to go ahead and I'm going to plug a 0 in everything, and I don't want to necessarily just assume that plugging a 0 in is going to yield a 0, although I think that's what's going to happen here. The arctangent of 0 minus 1/2 the natural log of, well, 1 plus 0 is 1, alright. So I kind of ran off the page there a little bit, kind of wrapped, but I think it works. Now, do you remember what the arctangent of 1 is? Hopefully you said pi over 4 minus 1/2 natural log of 2. I'm going to say natural log of radical 2, just to be fancy. And then minus, I do think these all turned out to be zeros, so just a whole big 0. So I'm going to say my final value of that definite integral is pi over 4 minus the natural log of radical 2. And what a fun answer that was. All right, our next example, I wondered if anybody's been sitting there at home the last few weeks wondering what in the world is the antiderivative of natural log. We've derived natural log. We said his derivative is 1 over x, but we've never integrated him, and it seems like such a simple function. It seems like by now we would have had a rule for it, but believe it or not, we haven't, and we're going to use integration by parts to actually integrate this rascal. And then once we get done integrating it this time, if you want to commit this one to memory, I would encourage you to do so. But of course, if you're not able to memorize it, that's okay. You could always go through the steps that I'm about to do right now in order to work it out in the middle of an exam. So what are we going to let u equal? Well, start right there with the L. U is going to be the natural log of x, so his derivative is 1 over x times dx. What's left over? What are you going to let dv be? That's going to be your dx. You'd already used ln, so dx is the only thing that's left. If you integrate both sides, v equals x. According to our rule, u times v minus the integral of v times du. Look at how nicely this one's going to clean up. This is absolutely a gem. One of my favorite integrals. Because these x's cancel, you're really just integrating 1 times dx, which is x. And then don't forget to throw your plus c on at the end. So ladies and gentlemen, the antiderivative of plain old natural log is x times the ln of x minus x plus c. Good one to maybe perhaps memorize, or if all else fails, you can repeat the steps I just did. Alright, I think it's time that we really got after one by ourselves here. So I'm going to pose one here on the screen. We're going to do the integral of sine, and that's going to be times the natural log of cosine. What an unbelievable function that is here. Okay, so what I want you to try to do is I want you to try to pick the correct u and calculate du. I want you to pick the right dv and calculate v all by yourself, and then go ahead and plug them all into the formula and see what you get for your final antiderivative, and then come on back and see if you got the same thing I did. Okay, for starters, as I went through my order, liate, I ended up letting u equal the natural log of cosine, whose derivative is negative sine over cosine. And what I'm going to do is I'm going to just call that negative tangent of x times dx. Alright, what was left over? Well, dv was sine dx. Don't forget this little dx, especially if it's a non-multiple choice question. They're going to ding us a point if we don't have that dx. And now if you integrate both sides right there, you'll get v equals negative cosine of x. Don't worry about the plus c, we'll get it at the end. Alright, u times v, I had negative, whoops, gotta grab the pen here, negative cosine of x, natural log of cosine of x, minus the integral of v times du. Now you're wondering, how in the world am I going to integrate this? We've actually got 3 negative signs, if that's not enough for you. So I had negative cosine of x, natural log of cosine of x, minus the integral of cosine. And then I rewrote tangent. I guess I didn't need to write it as tangent. I should have just left it as sine over cosine so that you could easily see these cosines canceling out. So we're really just integrating sine. So my final answer, we're already there. We're already done. These are pretty quick and snappy. They're not as bad as they look. The integral of sine is going to be negative cosine, which makes a positive right there. And certainly we do have a nice big GCF of cosine if you wanted to pull it out. Otherwise, we'll just leave our answer like this. Well, we've got one more to tackle tonight, and it is, of course, the biggest matter of the night. And it falls underneath a subtitle called Repeated Integration by Parts. Yes, repeated. We're going to have to use more than one round of integration by parts. Repeated integration by parts. And what you're going to find out here shortly is that the first round didn't get us quite where we needed to go, and so we have to reapply the rule. So let's take a look at the example. Let's try the integral of x squared times the sine of x. All right. So according to our chain of command, what are you going to let u equal? All right. I did not have a log function. I did not have an inverse trig, but I do have an algebraic function or a polynomial, so I'm going to let u equal x squared. Therefore, du is 2 times x dx. By default, dv has to be the sine of x dx, whose antiderivative is negative cosine of x. All right, so let's go ahead. We'll plug everything in. uv is going to give us negative x squared cosine of x minus the integral of v, which is going to give me plus cosine, times du, 2x dx. All right, so what's the big problem? How come, every point, by the time we got to this point and all the other problems, I had an integral that was easily integratable. The problem is I still can't integrate this. We're stuck right now. So what I'm going to do is I'm going to use another round of integration by parts here. So I'm going to do another basic setup. Let's see if we can slide the screen up just a little bit more. All right, now, when I do these assignments, I'm just focusing on this integral right here. All right, so I'm going to let u equal, again, the algebraic function whose derivative is 2. Now what you're going to find out is the good news is right now that the du does not contain an x. That's the good news, and that's how we know we've only got to do it one more time. dv by default is whatever's left over, and the antiderivative of cosine is sine. All right, so here's the first thing. Bring down the first term that you already had. So that's going to be negative x squared cosine of x. And then I'm going to switch colors. I'm going to do plus uv, which is 2x sine of x, minus the integral of v du. And finally, this time, I do have an integral that's very easily done. So we'll go ahead. We'll just put the finishing touch. Negative x squared cosine of x plus 2x sine of x. What's that going to be? I'm going to say positive 2 cosine of x is the antiderivative, plus c. Ladies and gentlemen, this is one of the coolest antiderivatives we've seen all year. I've repeated use of integration by parts, but it really wasn't that bad. So make sure, number one rule, walk into class tomorrow and make sure we know the formula. The integral of u times dv is equal to uv minus the integral of v du. We're going to make sure that our handwriting is sharp tomorrow. We're going to make sure that we can easily tell the difference between u's and v's when we look and read our paper. And we're going to make sure that we pick our u first according to the acronym LIATE, and then dv will be by default anything that's left over. So let's rock and roll. Let's really step up our game tomorrow and show them how it's done. We'll see you tomorrow.